Thanks a lot. So the title of the project is named Voice Bank for Alignment. Voice Bank is the name of the dataset I create, and I use this dataset to actually help the company to align the model to its business goal, actually. Yeah. And I'll divide the presentation into 5 parts: backgrounds, voice bank data site, alignment training, evaluation, and future plans. So let's first talk about a little bit about the company, Boson AI. So actually, this company now this year shifted a lot to the audio side. So the goal of the company is to build build some model understanding and generation model, and help the computers to communicate with humans easier and more natural. And the company currently has 3 offices, one in the Bay Area, one in Toronto, and the data center is in Barrie, the Toronto Barrie. And so 2 of the founders of the company, one is Alex, one is Mu. So and for this year, actually, the company has some breakthroughs and milestones on the audio generation side. So several months ago, it just released a new model named Higgs Audio V2, which is the 3B sized text-to-speech model. And this model has received lots of observations and is quite popular on Hugging Face, actually. And we also receive lots of interest from not only the customers, but also the individual contributors. Yeah. And also, Boson has released its new demo voice agent workspace on the right side, you can see. So maybe for this year or maybe for next year, they're gonna build more applications on top of their foundation models and help the customers to build their own voice agents. However, after publishing all of the models, they also received lots of comments and issues on probably the Hugging Face and also GitHub issue page. For example, lots of people are saying like the voice cloning ability of the model is not that good. So the voice cloning is something like you give it a kind of voice and you want the TTS model to generate the audio in exactly the same speech, in the same voice, right? So that's the cloning the voice. And they're also saying like the voice control ability of the model is not that good, it's not stable. So all of these issues are quite understandable because they just released the base model. And for the next version, for the next aligned TTS model, probably which is the Higgs Audio V2.5, we need more data and more algorithms to align the model to have better voice control ability. So that's the background of my project. And the goal of my project is to solve all of the issues mentioned. First of all, we want the stable voice clone ability to help the model to generate the audio in a similar voice to the prompt audio with the high success rate and similarity. And we also the second one is the best voice design ability. So if you give the model a text prompt to describe the voice, for example, a old male voice and with the high pitch, so maybe the model could just generate the voice exactly matched with the description. So this task is the voice design. And the third one is we want more demo voices to show our model to other companies, to other customers. Yeah. So based on this goal, and also based on already the alignment training pipeline we already built, so we just want to curate a data set to align the model with the 3 goals. So that's why we create this voice bank data set. So this data set is actually has 100K of the audio clip and description pairs. So the audio clip is just a clip of someone's voice, and the description, one of the example is on the right side. You can see there are lots of text, including the name of speakers, gender, age, category, language, accent, and transcripts, duration, style, speed, pitch, timbre. So all of the text actually you can remember are in this description. So with all of this pairs, other clips, and descriptions in this data sets, we want to use this data sets in several different ways to finally align the model to our three goals. And for the data set, we also have several goals. The first one is good audio quality. We want the audio to be very clear, no noise, and only with one single speaker. And also for the description, we want all of the text and information to be ground truth, not as little as synthesized as possible. And the third one is the most important one, good diversity. So we want all of the audio clips to cover all of the genders, ages, languages, or accent, which could help the model to be more robust and decrease the situations for the auto distribution. Yeah, that's the goal for the data sets. And after we have this voice bank data set, we can use some post-training algorithms to finally align the model to the final aligned model and also achieve these three goals. So that's basically the pipeline of the whole project. Yeah. And the first part is for the dataset collection. So actually, there are lots of sources. For example, for each language, and on the internet, there are lots of voice actor websites. So we just collect lots of real-world audio clips with accurate labels from diverse voice actors, not only from these two examples, but also from lots of other places. And also because for these websites, they're already in pair format. So one example, one description. So we just collect them all. And this kind of way of collection could enable the data we have is very diverse, and all of the texts are already ground truth. And after the collection, we add more labels to the data sets because we actually don't have the speed, pitch, and timbre, those kind of three labels by default. So we use some rule-based calculations for the speed and pitch, and also we use the model-based prediction for the timbre. And for the timbre, it's well to say that the timbre, we didn't like the model, use the model to predict the timbre from zero, like from the bottom. But actually, instead of that, we let the model to choose from the pair of timbres. So which one better describe the audio clips? We found that based on this way, the model could actually have a high accuracy and also less hallucination. Yeah. And on the right side, you can see there is a figure here. So here is the distribution of the pitch across all of the audio clips. Actually, you can see there are two spikes. So this is really natural because actually for the female voices, they have a relative higher pitch than the male voices. So probably this pitch, this spike is for the female, and this spike is for the male. So which means for our data distribution, our data is in a good shape and really diverse. Yeah, this is one of the proof. After that, we normalize all of the text because for each website or from each source, the texts are named and classified differently. So probably for one source, their age is classified in child, teenagers, middle, old. But for another one, it's classified as child, young, middle, old. So we just normalize all of the text, all of the classes. So finally, for this table, we just present all of the text, all of the features we have for the data sets. And you can see for the timbre, just like I just mentioned, we have the text in pair. So warm and cold, and rough and smooth, something like that. Yeah. And after that, we also wanted to enable the like to make sure the data quality of the data sets, right? So we have done lots of processing steps. For example, we just remove all of the background noises because from the source data sets, from the source web sets, all of the demo voices are probably for the entertainment or from the for the like the advertisements. So usually there will be lots of background noises and background musics. So we just remove all of them. And also we did a sentence level ASR, automatic speech recognition, uh, to finally get for each sentence its transcripts and also the start and end timestamp. And also we did the speaker diarization to assign the sentences to each speaker ID. And after all of the pre-processing and cropping, we also enable the audio length to be in 5 to 15 seconds because we found this duration range is in the sweet spot, which is enough for all of the use cases, but also won't cause a lot of burden to the model training. And we also checked all of the text enable for each other clips. We have all of the text we need. And for each clip, it belongs to only one single speaker. Yeah. And the final step is the distribution balancing, which in my point of view is the most important steps. So after all of the pre-processing, although the data set is already quite purified and also has lots of data, but the data set has unbalanced distribution, especially on age and accent. For example, for the child, before the balancing, we only had close to 1% of the child, and for the old, we only have 4%, which makes sense because for the all of the sources for those two types of people, they won't just put their voices on the website, right? So we can't just collect lots of their demo voices. But for the real use case, we want these two kind of age durations. So we want to balance those two categories. So we just retrieve all of the speakers using the speaker IDs and recut all of the audio clips and keep all of the clips for these unbalanced classes. And after this processing and balancing, in the green color, this is the current distribution of the data sets. For the child, we already have 4%, and for the old, we have 15%. And also for the other accents, like Chinese and Indian accents for English, we have 10% of the data. Yeah. And after all of the processing, here is the final statistics of the data sets. We have 100K of the audio clips, more than 200 hours, and for the audio clips, it's in average 8 seconds. For the gender, it's almost 50-50%, and for the age, for the style, for the speed and pitch, we all achieve the good balance of the distribution. Yeah. And up to this time step, I think we already achieved the goals, 3 goals for our dataset collection. The first one is accurate description because all of the texts are ground truths. We can make sure of that. And the second thing is diverse. You can see all of the balanced distribution. And the third one is audio quality because we have all of the pre-processing steps. We can also make sure the audio quality is good. So now, upon this time point, we have a really good to use, ready to use audio data set. Yeah. And the second step is for the training. And because of the time limitation and also for the company's focus, we only use this data set to train on the voice clone task as one of the 3 subtasks of the goals. So for the voice clone task, for this pipeline, you can see for this figure, this is how we use the data set to train the model. So for each training step, we just randomly sample the demo voices from the voice bank we just built. And using that demo voices and using one of the example sample from the text prompt text. For example, welcome to Boson AI. We just prompt the base model to generate several examples, synthesize audios, and based on several metrics, we did a reward calculation, and we just do the DPO or GRPO to finally train the aligned model with our goal. And for our case, we use three metrics to calculate the reward. The first one is named the word error rate. So basically is the accuracy of the transcript of the audio clips you generated. And the second one is similarity. Is kind of metric to measure how similar the voice you generated and compare with the voice you provided. So this is the directly matching of the voice cloning ability. And the third one is named MOS, which stands for the mean opinion score. So actually, we use some other models to judge the audio quality. So it will just rank the audio quality and give a score, scale from 1 to 5. 5 means the audio is good to listen, good to use, and 1 means that the audio is kind of a rubbish. Yeah, that's the basic pipeline for the training. And here are more details for the training. So for the training pattern, although we use GRPU, but we didn't use the real online GRPU because the first question is about the infrastructure. Because for the company inside internal, it has lots of restrictions. For example, the dataset format you used, and also the data processing pipeline. So if we use the online, it could work, but it's going to take lots of time, much more longer time for us to train a model. So instead of that, we choose to use a iterative offline GRPO. And for the synthesized data generation, we choose to select the batch size as 8. So for each step, we are going to generate 8 samples. And for the reward calculation, we used a combination of the MOS and similarity I just introduced. And after all of this, we collect all of the synthesized samples. We did a data filtering step because at the beginning part, the base model is not that stable. We want to make sure that for the iterative offline GRPO, it could also has some effects of the SFT. So we want to really control the training process of the model. So we just discard lots of samples, which is accuracy is bad, or for one group of samples, the sample with the best reward actually has only a little gap compared with the worst sample. Yeah, we just delete and throw all of these samples away. And finally, we pack all of the data and samples and cache them into a big dataset format, which is an internal format we used at Boson AI. So which is much more faster than the existing open source data format. And for the training details, we used a batch size of 128 on 32 H100s. And the whole training takes roughly in 6 hours for a 1B TTS model for 1 round. And for the iterative offline, we tried 2 and 3 rounds. Yeah. And one of the discussion also happened inside the company is why were we still using the GRPO in offline rather than the standard SFT? I think actually there are 3 reasons. So the first reason is the data limitation. So for the SFT, actually, we need the ground truth pairs of the voice cloning data. But actually, there's no ground truth for that. So the data belonging to one voice is really hard to collect because we can't say like, even in one sentence, the voices in one sentence from one speaker is exactly the same, right? Because the voice also depends on the timbre, the pitch, the emotions of the speaker. actually, we cannot just select randomly or have a kind of threshold. But for the GRPO, actually, because of the samples, so this kind of limitation could be solved somehow. And the second thing is less forgetting, because we only train the model for one specific task, but actually we don't want the model to forget other pre-trained or continuous pre-trained features. For example, the expressiveness or the emotions we trained previously, right? So if we use the relative on-policy data, we could somehow release or solve or reduce this issue a little bit. And the last point is about the flexibility. So after we generate all of the samples, actually we can reuse those samples. We can only just recalculate all of the rewards. So this can make the whole pipeline to be reused for maybe several times. So this is much more convenient than regenerating the data in the SFT. Yeah. And after all of the training, finally we did evaluation. Well, for the metrics, we still use these three: WER, similarity, and mean opinion score. And for the benchmarks, we use three benchmarks. The first one is CTTS from the Biden's seed. It is the kind of standard benchmark for the zero shot and few shot voice cloning. And the second benchmark is ESD TTS, stand for the emotion, something like TTS. So which emphasize the emotional and expressive variability. And the last one is the Cozy Voice 3 evaluation sets. We specifically we use the multilingual voice cloning subset of this evaluation set to try to evaluate our model on several multilingual settings. And here are some results. The first one is from the CTTS. You can see we compare with the previous Higgs V2 model and the Cozy Voice 2 model. And the third one is the VB GRPO, stands for the voice bank GRPO aligned model. You can see on all of the metrics, English WER, English similarity, English MOS, Chinese CER, and also Chinese MOS. So our model achieved the kind of better performance compared with all of the baselines. And also for the ESTTTS, it's the same case. Our model achieved the best the best performance across all of the categories, almost all of the categories. And which means after the alignment, the model actually improved a lot, especially for the WER, which means the model for the voice cloning task, the model is much more stable. And after that, it is the performance on the Cozy Voice 3. So for the Cozy Voice 3, actually it has, let's see, that's 9 languages, 9 linguals, English, Korean, Japanese, Chinese, France, German, Spanish, Italian, and Russian. So surprisingly, because we only trained our model only on Chinese, English, Japanese, and Korean, but actually it achieved a higher, a way much better performance also on German and Italian, and also on Russian. So this is quite interesting, which is quite as kind of astonishing. So we can see like the languages, the language is not like a single or specific. So actually, there are lots of kind of pronunciations or items of the song that could be borrowed from one language to another. So probably that's another reason why people decide to use IPA in their training for the language models, because all of the pronunciation and the words and letters for different languages are kind of same, like in the token level. And this is another kind of proof that our tokenizer or our encoder is really good. It could just extract all of the features from different languages and let the LLMs to learn all of them together in a unified format. Yeah. And the last evaluation results is the comparison between totally offline and the 2 rounds of iterative offline. So as you can see, definitely the iterative offline is way much better than the totally offline, which means the online policy is definitely better. So uh, currently, I'm still working on the real online pipeline, and probably it's gonna be finished very quickly by next week. Then probably if we have any new results or any new comparison, I can also share the following results in the channel or in our lab. Yeah. So after that, I want to show you some examples about the voice cloning ability our model could achieve. Uh, so let's start. Please let me know, can you hear it? So the first one is the prompt audio.
Specifically, the skills that are in demand relative to the supply of people who have. This year, companies are settling more towards talent with soft skills and hard skills are on the top.
And based on this prompt audio, this is the sound our previous model generated.
The sun rises in the east and sets in the west. This simple fact has been observed by humans for thousands of years.
And this is the new model.
The sun rises in the east and sets in the west. This simple fact has been observed by humans for thousands of years.
So basically, this prompt voice actually has a Indian accent of English. So basically, after the voice cloning alignment, our latest model could actually clone this accent successfully, and you can hear that the timbre, also the pitch of the voice is very similar compared with the prompt audio, right? Yeah. So here are some takeaways and conclusions. So the alignment training is highly effective, and also probably for the company, alignment and post-training is probably the most important part for now. And the second one is for the training language mixtures. Actually, the mixture of languages we train plays a critical role. For example, the cross-lingual transfer effects I just showed you guys across a full set of Cozy Voice 3 languages, right? And also another interesting point is we found the large proportion of the Chinese data during the training actually surprised the English performance, but could improve the Korean and Japanese, which makes sense. But during training, we have to really make sure how we decide the training mixture of those languages. So this is a little bit tricky. And in the future, I think we have to try some dynamic mixture reweighting methods. Yeah. And the last one is the reward hacking. It is actually have to be carefully managed. And also is another reason why we didn't include the word error rate in the reward calculations, because actually a pretty low word error rate may lead to slower and overly conservative speech with reduced expressiveness. So the model tried to speak something like really, really slow but very clear to achieve a really high WER, which is not something we want. We want a model to perform very naturally, right? So this thing is also have to be considered carefully. Yeah, and for the future, online training is a must to do, and it's the things I'm currently doing. And secondly, we want to include more data resources to make the model more robust and to have better performance on the benchmarks. And also we have to try other subtasks like the voice design and maybe for the paralinguistic generation, also something we want to try in the future. And in the end, I want to have my special thanks to my academic supervisor, Professor Jing, and also my industrial supervisor and the whole team of Boson AI, and also the funding support from MyTex. Yeah, that's all of my presentation. Thanks.
Thank you so much, Wentao, for the very nice work. Yeah, great job. And I want to ask a bit about how you innovate. Is it a lot of process of trying different methods that have good reputation and running them on your setting? And maybe half-half in terms of trying different RL and cleaning the
Yeah.
data and creating different data?
Yeah. So basically, I think the distribution of the time I spent on each part is for the first 4 months, I did the data collection and all of the cleaning, all of the purifying. And for the later 4 months, I just tried different settings of the training. For the training, we tried the DPO, offline DPO, iteratively offline DPO, offline GRPO, and iteratively offline GRPO, these four settings. And finally, we found the iterative offline GRPO performs the best. And also we tried different a mixture of the languages, as I mentioned here. So because we have four languages, English, Chinese, Korean, and Japanese, so trying different mixture of the languages actually takes lots of times. And also because for each trial, we have also tried to use different like the parameters, and also all of the amount of data we use. So it also takes a lot of time. And the last part is how could we like the model to perform the feature we want, but don't hurt other kind of features, because finally we want to release a kind of balancing model. So all of these trials take lots of time, and I think that's also something I learned from the industry. It's not it's not something like the really in the academic. We can just have the best performance and that's it. But for the industry, we have to make sure that there's no latent issue. Every part of the model should be tested thoroughly, and then we can release the final version.